So our next speaker is Peter Juarez. Mr. Juarez is a research engineer at NASA Langley Research Center, where he's leading an effort to apply non-destructive evaluation modeling and analysis to the design process for aerospace structures. Today, he's going to present applications for inspection simulation at NASA. So our next two speakers, I'm sorry, I should have said this before. Our next two speakers are going to be presenting remotely. So when we do questions, I'll probably just relay the questions to them from up here, but thank you very much.
Great, thank you. Like she said, my name is Peter Juarez. Today I'm going to be talking about computational non-destructive evaluation case studies here at NASA. So we'll go ahead and jump right into it. First, you can change. There we go. I want to thank Star for her excellent presentation previously. Everything that's going to be presented in this instant presentation was made using the CFS simulation software. We really like that software here at NASA. And because Star went first, she did a lot of the legwork, which takes a lot of the pressure off me in presenting this.
Sorry, Peter, we can see the Zoom chat or the Zoom participants in front of the slides.
Really?
Yes.
That is not on my screen. I think that might be on your screen.
I'm sorry, my bad.
No worries. So we're using CFS simulation software. In my branch, I would also be remiss if I didn't also mention that we do a lot of development of our own in-house code for simulation. And while CFS is great for many applications and has a lot of convenience functions, sometimes we find it's good to also write our own code for simulation, because that way we can tailor specific simulations for specific applications. And we also have access to all the nuts and bolts of the code, we can also tailor it to run as fast or as accurate as we want for the application that needs it. So in general, there are three situations where simulation of inspection really can come into play. And so that first situation is when you can't physically perform the inspection yet, something's preventing you from doing that. The second is you can perform the inspection, but you don't know how you want to do it yet. And the third is you can perform the inspection, you know how you want to inspect, but you want to know more about the resulting data. And there's some other cases beyond that, but these are the three primary ones that we've identified. I'm going to give you examples of each of these three scenarios. And because it's easier to tell a story, I'm going to start with the third one. When you can perform the inspection, you know how you want to inspect, but you want to know more about the resulting data. An example I'm going to be talking about today is a probability detection study on friction stir welded panels. So friction stir welding is a kind of a rare and complex type of welding process that's used mostly in metals that if you heat them up past the melting point, they start precipitating some of their alloy elements, and those are not. You want to keep those in the metal so you can retain its properties. You don't want solid inclusions of like copper or manganese in your welds, and so they're used often in types of aluminum alloys, especially aerospace grade aluminum alloys, specifically, we have a space launch system that NASA is working on, where the barrel section is actually joined all together with friction stir welding. And the process of doing that is they basically take a spindle, plunge it in between the space of two adjoining panels, and then spin it really fast. And the friction of that spinning and the mechanical actuation will actually sort of meld and mix the metals together very close to melting point, but not exactly melting. And the result is a very strong weld that retains the properties of the aluminum alloy and a kind of a complex grain structure on the inside. So anyway, we have this core section, everything's friction stir welded. We need to inspect all of these. On most applications do with aerospace, especially with welds are 100% inspected to make sure that they were created correctly. Star mentioned this previously in previous talk. And then the way to qualify those inspections with a probability detection study. And Star talked about this already, but I'll just reemphasize, these are a very crucial study to the safety of the structure. It's basically you create curves like this that say given a certain aspect of your defect, this is the probability you're going to detect it. And so the study that we got, so we received this data for this probability detection curve and the experimental data of all the scans, and we were using it for a different purpose. We were going to try to do something called model assisted POD, which I won't get into here, but we can talk about it afterwards. But there were some problems with the data that we got from them. Specifically, if you look at the bottom axis of this curve, it's the square inch area of the defect. It was a crack-like defect. And so when they were taking the data, they like Star mentioned, you make a whole bunch of samples of representative geometry and representative material, and then you put a bunch of defects into those samples, and you spread them out in the design of experiment sort of way, so you get a statistical representation of a normal inspection in your experimental data. And so these were machined using electric discharge machining, which basically they plunge a wire that they run a lot of current through, and you can make these very fine line notches in your panels, and those are supposed to simulate cracks. And so one of the issues was, though, that there was some ambiguity on to what the shape of the final notch really looked like. Ideally, we wanted a perfectly sort of rectangular notch like you see on here. But because the wire is kind of flexible and it's not a perfect process, several other shapes were possible. And all these shapes are going to change what your square area of your crack is going to be. And as a result, it's going to change the accuracy of your x-axis of your probability detection curve. And so when they processed the data, they basically made POD curves for a bunch of different scenarios. If it has a concave, convex top, if it's perfectly rectangular, and what is the probability detection given that. And then ultimately, in practice, you would just go with the most conservative POD curve that came out of that. But we can do a little bit better. And so we went through the UT data and we found some signatures that would normally be ignored. And we could see the crack pretty well. It had a clear definition of what the crack was supposed to look like in the UT data. And so we decided to use simulation to answer the question of what the crack actually looked like, or what the notch actually looked like. And so we simulated several different types of notch geometries and found out the only one that really matched the data was the perfectly rectangular notch. So with that, we were able to define that the POD curve was accurate if we use this square area to estimate the notch size, and thereby enhancing any sort of risk analysis that might be associated with this POD curve. And so, yeah, that's just an example of where all the data has been collected. We don't have to do any more experiments, but we can dive deeper with simulation to uncover things we wouldn't normally be able to uncover just by looking at the data or inspecting it in different ways. So the next scenario is when you can perform the inspection, but you don't know how. And the example I'm going to talk about today is inspection of high-capacity multi-layer pressure vessels. So across NASA agency, we have, I think it's about 250 of these types of high-capacity multi-layer pressure vessels that are seen here. We use them for a whole bunch of different applications, some for wind tunnels, some for material testing, but they're scattered throughout the agency, and they were all built around roughly the same time, 1960s, 1970s. And they're great for what they're used for, and we hope to use them for a long time to come, because if we wanted to replace all these, it's on the order of billions of dollars to replace all these. Unfortunately, because they were built so long ago, they were actually built before the standard existed to make these type of pressure vessels, and so they were built with a design mentality of just, if we over-engineer it, it'll be safe enough, which works for a long time. But unfortunately, we need to certify that we can continue to use these with some sort of analysis and inspection regime to make sure that these are in fact safe to use this late after they've been manufactured. And the motivation for that is it didn't happen at NASA, and I don't think it's happened in the States, but overseas, these type of pressure vessels have have failed before. And because there's such a high capacity and such a large amount of energy in these vessels, when they fail, the catastrophic failure can take out buildings near it. In fact, one of the safety precautions they have for these type of vessels right now is if they are anywhere near buildings, and when I say near, I mean within a few blocks of buildings, there has to be a sort of a mound of concrete or boulder structure in front and behind of each pressure vessel, because the idea of if the head pops off, you have all of a sudden a sort of a missile that's traveling very fast and is very heavy, and they want it to hit that before it hits any structures. And so that's the type of energy we're talking about, and that's the type of safety concerns that we're talking about in order to continue using these. Now the problem is, you saw some weld inspections on STAR's presentation where you have two plates butted against each other and then you have a little weld in between, you inspect them. For multi-layered pressure vessels, you have a lot of these concentric steel plate rings that are wrapped around the vessel, and they're joined together with this one monolithic weld in the center. And so as you can imagine, if I have a defect or a notch down here, and I'm trying to inspect from the top, the only path to get down here is through the weld metal, which is a very complex multi-pass weld structure that's not easy or intuitive to understand. And you can't pass ultrasound through the plates because they're touching each other, but there's such a acoustic impedance mismatch, all the energy is going to just get reflected away. So this is the only way to do it. And so just intuitively, this isn't something we inspect every day, so we don't know how we would approach something like this. And so our branch was approached to try to help development of this inspection technique using simulation. And so using simulation, we validated that we could simulate this inspection, and we were able to show that we can represent reality in SIVA for this type of weld. And then we went about testing a whole bunch of different configuration techniques and types of settings on your probe, what kind of probe to use, different delay laws, and different sort of orientations of the probe, until we finally narrowed down a set of techniques that would be good for finding defects in this weld. And we had two focus areas. One was the head to weld inspection, which is this monolithic one where you do have access to the side, and then the shell to shell weld where you only have access from the top. And so that head to shell weld is pretty straightforward. Really, you only have to contend with the very complex grain geometry that you have in that weld and make sure it doesn't steer the beam into a complete off kilter direction. But then the shell to shell weld is a little more difficult. In fact, if you're just looking at this, like this is supposed to be a straight line of acoustic energy for the ray trace on here, and it's very, very wavy. In 3 dimensions is actually arcing sort of in and out of the centroid of the weld before it gets to the bottom. But then we found out that we can detect certain defects looking at it differently. Instead of looking for an indication, we can actually look for a lack of indication, and that would tell us that there's something there reflecting signal away from the transducer, and then we can infer the size and the depth of that to a presence of a crack. And so that was one of the techniques we recommended. But we also are able to do sort of a gamut of different types of defects and different parameters on those defects to see what it would do to the quality of the signal when they're doing the inspection. And so if we are simulating just sort of this flat, very straight like crack, if it's tilted in one way or another, this is the type of signal you would get back in return. And you can see that even just 10 degrees of tilt, you're already minus 15 dB, which is a pretty significant amount of energy not coming back to your probe. And then if you have a sort of branch structure, which is a little more realistic, then you actually get better signal. And so, if you have a large aggregate crack, which produces these branch structures, then you're actually in a better chance of finding your defects. And so the last situation I'm going to talk about is when you can't physically perform the inspection yet. And the example I'm going to talk to is the on-orbit inspection of welds on the International Space Station. So The International Space Station, as you know, has been up in low Earth orbit for a very long time. It's entirely metallic structure, welded metallics, mostly aluminum alloys, built by a variety of different countries, and they were all sent up at different stages. The one of the oldest modules is the one that's called Functional Cargo Block. It's actually a Russian module that goes by the Russian initialism FGB, and it's shown in that red circle right there. It's been up there for about 22 years, and it's starting to show its age. So the structure itself, all structures on the International Space Station have a certain certification of use, and those certifications have an end date. And for the functional cargo block, that end date is 2028. And obviously, we want to use this past 2028 for at least a few more years after that. But we need to recertify that this is safe for habitation if we want to keep habitating it. Now, during the process of certification, we do a bunch of structural analysis and a bunch of physical testing. And through the FEM analysis, we were able to locate that a particular weld called weld 33 had the propensity to produce a lot of fatigue cracks just by the normal cyclical loading that's experienced by the space station. And in particular, if a fatigue crack grew to a certain width, they projected that it would cause a complete unzip of the structure, which would then vent the atmosphere and disconnect that structure from the rest of the modules, which is obviously something that you don't want to happen for the space station, especially when people are in it. To make matters worse, there was a ground test article that was fatigue cyclic loaded to similar loads that were experienced by this module. And when they inspected that well on the ground test article, they found pretty alarming size cracks in that weld that, though it didn't cause failure, could be predicted to keep growing that would eventually cause failure. And so to certify this for continued use, we have to inspect the actual structure, which is in space. And the plan to do that was using ultrasonic inspection from the inside using a handheld probe. So we were approached by Johnson Space Flight Center that they'd heard of our work using ultrasonic simulation of ultrasonic inspections, and they asked us to help in the development of a technique that would work in this scenario. So we had a lot of challenges in this task, and one was working with incomplete information. In particular, first mechanical drawings we got were just this, which is just pen on printer paper. We eventually got better ones, but these are the ones we had to work on for the time being. Also, when they gave us the material, they just told us the name. It was a Russian aerospace grade aluminum alloy, and as you can imagine, Russian aerospace grade aluminum alloys aren't really easy to determine the material properties from. You can't really just readily Google that. They're not published that much, and if they are, they're usually published in Russian. And to make matters worse, a lot of the parameters we need to simulate ultrasonic inspections are not the same parameters that are needed to perform engineering calculations. And those are the ones that are the most readily available, things like Young's modulus and things like that. And so we had to do a lot of clever things to not only gauge the uncertainty that came with all this incomplete information, but also to look at other things that we did have material properties for and sort of find what's close enough to give us the right answer. And so it gives us a little bit of different mindset of instead of trying to find the right answer that's perfectly represents reality, you just need to get an answer that's close enough to answer the question that they're trying to ask. And in this case, for the first round of it, it was, is this feasible to do? And with that information, we were able to do that. And then for more specific questions, we needed a little bit more accurate information, but we're still able to make do with some of the gaps in that knowledge, knowing that that we only had to meet certain goals in order to answer those questions. A couple more things that we were given. We were given some pictures of what the structure looked like and the inspection area. And then we also went and found images of our own of the inspection area to make sure that the inspection equipment could even fit there in the first place. And so that's the inspection area is right there in the red circle, and these are close-up images of it. And one thing you'll notice is that there is a sort of a canvas fabric-like covering over most of the surface of this module. And in fact, most of the space station is covered with this type of fabric, either this type or a different type. And all these, in this area in particular, all this fabric was adhered to it using a layer of adhesive that's 22 years old at this point. And so we knew ahead of time that they were going to have to rip up this fabric and then we'd have to inspect through it. And so one of the questions they asked was, okay, if we rip up this fabric and there's a layer of adhesive left over, what's that gonna do to our inspection? And do we need to get rid of that layer of adhesive? And the reason that they asked that question instead of just like getting rid of it is because in order to get rid of it, you'd have to do a couple things. You'd either have to use some sort of solvent, which in the space environment, a zero-G environment, that's problematic by itself, or you'd have to use some sort of abrasive method, which creates dust. And depending on what kind of adhesive this is, that could be problematic. Also, you don't want to have that happen. And so they wanted to avoid that at all costs, but they also wanted quality inspection. And so before going up there, they wanted to figure out, what's the best course forward. And so to show you that, how we answered that question, I'm going to stop sharing for a second, and I'm going to bring up the actual simulation we used, or a similar one. And one second. Okay. All right. And here we go. So this is SIVA. You saw it in the previous presentation. This is sort of a live image. And just to confirm, everyone can see my screen right now, right? I will take your silence as an answer.
Yes.
So, yes, okay, perfect. So this is sort of what these structure look like. It's not a perfect representation, but here we have several types of little notches here that's supposed to represent cracks. Go away. And we have an ultrasonic probe where I can move it. The simulation's already been performed, so we're just looking at the data. And this is what's called a B scan. Some people call it an S scan of the data that comes back from the probe. And you can see I can just drag it right here. And this is essentially what the inspectors would be seeing when they're doing the inspection. So simulation is a really powerful tool to get people ready for what inspection would look like, which is vital for space-based inspections because it's astronauts going to be doing it and not actual inspectors. But it's very useful to make those sorts of images to help prepare them for what to look for. And so anyway, we're going to focus on this crack right here. And so there's two notches, one here, one in the bottom. This is the indication from the notch in the bottom. This is the indication from the notch in the top. And if that's not clear why it's mirrored like that, I can show you by folding the image. And so now the image is reflected to show the true path of the ultrasonic energy. It bounces off the bottom, then hits the top, and then bounces back, sort of like what you're seeing right here. And so this is a simulation of an inspection under perfect conditions. There's a little bit of curve to the part, which is causing a little bit of a coupling issue, but the surface itself is fine. Now, if I simulate it with 0.1 millimeter of adhesive on there, it's very, very hard to see. But let me do this. Oops. Now it's upside down. In the cross section, you can see there's a very, very fine layer of adhesive between the probe and the rest of the part. Zoom in. It's this right here. So very fine. And we tested several different thicknesses of adhesive, and the answers were mostly all the same. But this is the smallest one we tested. And even with the smallest one, this is the same indication. Let me put it back over there. There we go. So both these images have been scaled to the exact same amount, and you can see a drastic reduction in the signal quality just from a very thin layer of adhesive. And there's a couple of things to take away from this. One, we're doing a sort of an ideal simulation of what the adhesive would look like. In reality, it's actually going to be patchy and different thicknesses, and so it's actually going to be worse than what we're looking at right here. So this is like best case scenario. Um, and the reason that this happens is because there's such what's called an acoustic impedance mismatch between the probe, the adhesive, and the rest of the structure. And what acoustic impedance mismatch means is basically how much energy gets transmitted and how much energy gets reflected when it interacts with the interface between these two materials. And so there's such a difference in acoustic impedances. A lot of the energy gets reflected back at the probe before it can get in. And then when it's coming back out of the structure because it reflected off something, even less is getting past the adhesive and then getting back to the probe. And so we get instances where a lot of these defects are as close to the noise floor as we can imagine, and to the point where I would not say confidently I'd be able to find these in the field because of how much the signal quality went down. And we simulated up to like 1 millimeter layer of adhesive, and it was, I mean, the results are just as bad as you can imagine for that. And so with this, we were able to bring evidence to the people that were in charge that under no uncertain terms, you need to remove as much adhesive as possible if you want to have a quality inspection. Um, and yeah, that is my presentation. I'll go back to the slide deck, but are there any questions?
Yeah.
The bottle fields, or the bottles that he first was doing some analysis on, can those bottles now be certified to be, inspected and pressure rated and things like that?
The question is about, were the overwrap pressure vessels eventually recertified? Is that right?
Yes, they were. It was a very long process, and the inspections, I think, so that work started in 2018, 2019, and they just finished in like 2022. So it was a very long process because there's so many of them and there's so many welds, but they were able to certify a majority of them, and then some of them were set to be retired anyway. But yeah, so the majority they were certified.
I'm at Langley also at the 800-foot itinerary tunnel, and we've inherited somewhere between 5 and 10 of those bottles from another facility. And eventually we wanted to incorporate them into our air storage to increase our runtime. And I don't know if there's any way we can get those bottles inspected, and we'd like to eventually come up with a design in order to increase our runtime by incorporating these bottles.
Okay.
How?
Yeah. So I think the inspection regime only included ones that were currently in use, and so if those weren't in use already, then they probably weren't inspected. But the people who did the inspections are still around, and I think they're still able to do that inspection. So I can get you a contact information of the people who are involved with that.